All right, I'll get started. So welcome to the re-recording of Lecture 9. Thank you for everyone who showed up. So this is, again, I recorded Lecture 9, or I presented it live, and then the recording was messed up, so I'm re-recording it now. And I'm also going to take a slightly different approach, which is that I'm going to, instead of using my slides that I prepared for this lecture, I'm going to be writing some notes down live. So people seemed to like that the time that I did that, so I'm just going to continue with it now. Let me just get my full page drawing thing going. Okay. So last time we talked about solving systems of linear equations. And in particular, we looked at equations that look like ax equals b, where A is going to be a matrix, and B is going to be a vector in Rm. So you've probably seen these in your algebra classes, but you may not have seen until last week them written quite this way. But every linear system can be written in this way. Now it turns out that not all linear systems are created equal. Some are more important than others. And in fact, perhaps the most important linear system is the system that looks like ax equals 0. Now, it might seem kind of strange that this is like the most important system, but it is. And so we give it a special name because in mathematics we like to give important things their own name. And so we call this a homogeneous linear equation. So this is not homogeneous. This is homogeneous. And this is a different word. I had a professor tell a story one time that he was at a conference and he kept saying homogeneous instead of homogeneous, and he had like 3 people at the end of the lecture or the presentation come up to him, and then also like 17 people emailed him to correct him. So this is not something that you want to make a mistake on. It's homogeneous. And there are some interesting things about this system. For one, it's always solvable because A times 0, the 0 vector, is always going to give you back a 0 vector. So there's always a solution to this problem. And because of that, we call this solution, the solution x equals 0n. This is called the trivial solution. And so what we're really looking for is non-trivial solutions to this problem. And we will call the set of all solutions, so the set of all x in Rn such that ax equals 0m, this set is called the null space of A. Now, some people write null space as 2 words. I write it as 1 word. I think it's actually more common to see it as 2 words, but I think actually it makes more sense as 1 word, and so I'm going to use it as 1 word. And just because it's easier, we're gonna abbreviate this null of A. Or sometimes I'll just write null A with no bracket. So, I've called it a null space. So let's deconstruct that a little bit. Well, null here means 0. and I call it a space because it turns out that null is actually a subspace. It's a subspace specifically of Rm. Rn. Because, right, we have A being an M by N matrix, which means that if we have AX equals 0, then X is in Rn. Right, and so it's the set of all solutions in Rn. And to see that it's a space, what you can realize is that if I have two solutions, say AX equals 0n and AY equals 0n, then A times alpha x plus beta y will be equal to alpha ax plus beta ay, and these are both 0. So this is just equal to 0. So if you take any linear combination of two solutions to your null space problem, you get back a solution, and this is what it means to be a subspace. Now, as we've talked about, being a subspace of Rn means that null of A is actually equal to the span of some vectors v1 through, let's call it vk. Right, and these vectors vi are in Rn. Now, I'm not going to go into how we actually compute these vectors right now, but you can do it, and we'll talk about it in a bit. The first thing I want to talk about is some of the implications of the null space, and particularly why the null space is so important. So here's the question, right? We know that a linear system has three possible behaviors. If we have AX equals B, there are three possible behaviors. One, this has one solution. Two, it has no solutions. And three, it has infinitely many solutions. Those are the three possibilities. So right now, we really don't have many tools to figure out which of these is true. Like, even if you can find one solution to your problem, how do you know, how do you find all the solutions? Or how do you know if there will be infinitely many solutions? And I want to basically show you how you can use the null space to eliminate option 1. And so what do I mean by that? Well, in particular, suppose that null A is not just 0, right? So we mentioned already that null A, the null space of A, must contain 0 because A times 0 equals 0. But we're basically saying assume that it's not just 0. So in particular, we're assuming that there is some x such that AX equals 0 and x is not 0, right? So this means automatically that this system of equations has infinite solutions because we can take any multiple of x, right? So if we have A times alpha x, this is alpha ax, which is alpha times 0, which is 0, right? So, already we have infinitely many solutions. And it turns out that because of this fact, we can now guarantee that every solvable system must also have infinitely many solutions. So how do you show this? Well, we've already assumed that AX equals 0. Now suppose that AY equals B. So AY is a solution to the system of equations AY equals B. So Y is a solution, I mean. Well then, AY plus X is equal to AY plus AX. This is 0. And this is B. So this is B plus 0, which is just B. So just by adding X to Y, we get back yet another solution to our problem. And because we could add any alpha Y, or alpha X, I mean, because we could do A of Y plus alpha X, this means that we actually have infinitely many solutions to this problem, right? Because we can take alpha to be any real number, and so now we have infinitely many solution vectors. All vectors of the form Y plus alpha X are solutions, right? So just by answering if the matrix A has a non-trivial null space, we've already figured out that every solvable system has infinitely many solutions. So that means there's only two options. Either your system, as long as you have a non-trivial null space, so as long as your null space contains at least one non-zero vector, then every system has either no solutions, or every system AX equals B has either no solutions or infinitely many solutions. All right, so we've eliminated that third option. Are there any questions so far? Okay. Cool. Now I've said that basically we can use the null space to figure out that AX equals B has infinitely many solutions. But it turns out you can also use the null space to find all the solutions of AX equals B, right? And so to use this, we'll have to introduce some clever notation. Again, we're going to assume that AX equals 0. And we're going to seek all solutions to the system of equations AY equals B. Okay? It turns out then that the set Y plus null A is going to be the set of all possible solutions. So what do I mean by this set here? Well, we're going to define this set. We're going to define this set to be equal to the set of all sums x plus y, where y is exactly what we were talking about. So AY equals B, right, up here. Now we're not going to write that, but that's true. It's a set of all things, and the constraint we're going to have is, well, we're just going to require x to be in the null space. Sorry, null of A. Right. And so it turns out that this set of all sums between things in the null space of A and just a single solution to our system is actually all possible solutions to this system. Now, I'm not going to prove that to you, but I think it's very powerful that all you need to find the solution set to any linear equation is the null space of the matrix, and then any single solution to that problem. I think that's really cool. And it's one of the reasons why the null space is so important. Now, computing the null space is a little bit funny. It's not super intuitive why it works, but I want to go over it still because Ethan's going to talk about it in lecture 10. So the first thing we have to talk about is, well, we've talked about Gaussian elimination, but there's something we haven't talked about, which is called reduced row echelon form. Now, I'm not going to write down the full word because you'll never see it, well, almost never see it written out. Sorry, I got a cough. You'll almost never see it written out fully. So it's reduced row echelon form. You can see it written out in my notes that I posted in the chat, but basically a matrix is in reduced row echelon form if it looks something like one, and then this star here just means like anything. 0, 0, 0, 0, maybe a 1 here, maybe something here, dot, 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 0, 0, 0, 0, dot, 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 1. Right. So importantly, beneath every 1, there are only zeros. And so these leading ones, actually, beneath every leading 1, there's a 0, only zeros. These leading ones are called the pivots. And being in reduced row echelon form means that both above and below all these leading 1s in every row, there are only zeros. And actually, secretly, what Gaussian elimination does is it takes a matrix A that is not in RREF, and it sends it to a matrix B that is in RREF. And so that's all it's really doing. And critically, this process of sending A to B does not change the solutions to our problem when we're talking about AX equals 0. Right? Because what did we do when we used Gaussian elimination to solve linear systems? We had to do the same thing we did to the left-hand side we had to do the same thing to the right-hand side as we did to the left-hand side. But doing any of our row operations to 0 will keep it 0, right? If I have the 0 vector here and I swap 2 of the rows, it's still 0. Right? If I multiply any row, it's still 0. If I add any row to any other row, it's still 0. So we don't even need to form the augmented matrix to solve the null space equations. We just need to get A into reduced row echelon form. And so, in particular, this matrix A and this matrix B have the same exact null space. Which means that if we want to compute the null space of a matrix, we can just use Gaussian elimination to put it into RREF, and then we can just solve the null space equations by hand if we wanted to. So here's an example of that. Suppose I have a matrix that looks like this. Okay, if I want to solve the null space equation, I just need to form this equation. There's going to be 3 variables, x, y, and z. That's how I write my z's, don't judge me. And we want to solve for this equaling 0, right? Okay, we multiply this out, we get x plus 0y plus negative 2z equals 0. We get 0x plus y plus 6z equals 0. And so we can solve. And we can get that x is equal to 2z and y is equal to negative 6z, right? This should all be like review algebra. But oh, that's a 6. My bad. I do not write my z's as 6s. That was just a mistake. So our original vector looked like this. But now we have basically solved for the first two variables in terms of the third. So this whole thing is just equal to 2z minus 6z, and then just z, right? And this is equal to 2, negative 6, 1, z. So it turns out that the null space of this matrix is just the span of this one vector, 2, negative 6, 1. That's the whole null space. Because, right, like this is all possible solutions, and look, it's the span of a vector. So this is basically the easiest example I could find, but this kind of method does work. And if you get these more complicated matrices, you might have more than one variable left over at the end. And then you'll have maybe a 2-dimensional null space or a 3-dimensional null space, maybe a 10-dimensional null space or a billion-dimensional null space, right? And so all this stuff very quickly gets out of hand, and we no longer want to solve this by hand, basically. So what hope do we have? Well, this is both a math class and a programming class, so it's good to have some sort of algorithm that we can work with. And well, it turns out that there is an algorithm. It builds completely on things you've already learned. And actually, surprisingly, it works entirely using the transpose. So we're going to calculate null A essentially only using the transpose of it. So here's the steps. The first thing we're going to do is we're going to take A, transpose. Very important we take the transpose. And we're going to form the augmented matrix where we just add a full M by M identity matrix onto it. So if A, maybe this would be like 1, 2, 3, 4, 1, 1, 0, 0, right? That would be one example we could do. Now, the next thing we do is we're going to use Gaussian elimination to put this A transpose into RREF, right? And so this is going to give us a matrix that looks like B, C. Okay, and so this is still an M by M matrix, and this is still the same size matrix as A transpose was, right? And so we use this. This is Gaussian elimination. Gauss. Cool. So now we got this new matrix here, but some of the rows of B might be entirely 0, right? So you could have, B might look like 1, 0, 0, 0, 0, 0, 0, 0, 1. Maybe B looks like that, right? So what we're going to do is we're going to take the rows of C that corresponds to these 0 rows, right? And so I'm going to call them R1 through RK. And these are the rows of C that correspond to the entirely 0 rows of B, right? So maybe C, in this case we have over here, maybe this was the augmented matrix. Maybe C was, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is the vector we're going to take. And there might be more than one row, but we have these rows here, and we're basically done. it turns out that null of A is just going to be the span of R1 transpose, comma, through RK transpose. So just from this kind of very simple recapitulation of what you've already learned, you can already compute the null space. Now, implementing this in code is a little bit more tricky, but it's a pretty simple algorithm. You could do it by hand if you wanted to. I'm not going to because it's too long. So that's the null space. Now it turns out that there's more than one type of important space associated to a matrix. We've already talked about one, which is the null space. The second important space is called the column space. And what the column space is it's actually the set of all B, of all B and Rm, or Rm, such that this has a solution. Now, maybe it has more than solution. Maybe it has more than one solution, but it must have at least one solution. And in this case, the space of B's is what we call a column. And the column space, which we're going to call col of A, though I don't think I've actually used this in any of my future notes, is actually just, sorry, my headset disconnects after 30 minutes of no one talking, or I'm not receiving audio, so it disconnected. The column space is actually just the span of the columns of A. So I'm going to call these the columns of A. And so this span is the whole column space, right? So that's actually pretty easy. Now you don't really want to work with this span, so what you do instead is you compute Gram-Schmidt on these vectors here, and you use that as your you use those as your spanning vectors. So Gram-Schmidt comes back again, but that's not particularly hard to do, right? It's basically everything you've already learned. So the column space is kind of pretty easy to understand. And it turns out from just these two spaces, you actually can get 4 spaces. And these spaces are called the 4 fundamental spaces of a matrix. Now, only 2 of them are really important, at least when you start out. I actually do use all 4 of them at this point, but I'm kind of weird, and I do weird things. So the 4 fundamental spaces are, the first one is the null space. We've already talked about this. The second one is the column space. We've already talked about this. The third one is the so-called left null space, which I do not think I gave a symbol, but I'll just call L null. So L null of A, and this is just a null of A transpose. And then the fourth is the so-called row space. And this is just the span of the rows, but that's also just the column space of A transpose, because what does the transpose do? It switches rows and columns. So the row space of A is just the column space of A transpose. And that's kind of it. The null space and column space come up all the time, and they're basically paired. There's a way of thinking about the null space as essentially the information that you lose by multiplying by A, and the column space is the information you keep by multiplying by A. And so these two are also paired, and the left null space is the information you lose by multiplying by A transpose, and the row space is the information you keep by multiplying by A transpose. That's one way of thinking about them. Now, like, what does information mean? It's kind of this nebulous concept for now. There is a formal way of describing it, though. So that's it for this lecture. Thanks for listening. I'll stop the recording and people can ask questions.